Hello, SWIC Earth Science students, and welcome to the next recorded lecture. In this lecture, we are going to be talking about the atmosphere and an introduction to weather. So we're going to be looking at Chapter 16, which is the atmosphere, composition, structure, and temperature. The textbook goes into a lot more detail about atmospheric structure than I'm going to go into. I will admit I am not a meteorologist. I am looking at the atmosphere more for how it impacts weather and then how it impacts climate. So weather versus climate, what are the differences in these two topics? So they both impact the atmospheric conditions. They both talk about the atmospheric conditions. The difference is the scale. So weather are going to be the short-term, immediate atmospheric conditions in one spot. It is constantly changing. We see that around here all the time that, we might have snow in the morning and then it's nice and sunny and warm in the afternoon. Climate, however, are the more long-term patterns. So we are looking at temperature and precipitation over annual periods in a region. It will change much slower. So climate is not looking at a single moment, it's taking into account the entire season and the overall patterns. So if we look at this image, we see for a given location the yearly record lows, record highs, and then the average lows and average highs. So these records are going to be an indication of weather. These are abnormalities basically, whereas the averages will show the typical pattern. So this is going to be more indicative of climate. Weather is going to be driven by energy. So energy can be thought of in multiple ways. We have potential energy, which is stored energy. We have kinetic energy, which is the energy of movement. And then we have heat energy, which is kinetic energy of atoms that generates heat. There are two ways to think of heat. We can think about sensible heat. So this is the heat we can measure with a thermometer. And then latent heat, which, apologies if you can hear that. My dogs are deciding to play in the background. Latent heat is the amount of heat that gets absorbed or released when we change phases. So phases is the state of matter. So we have 4 phases. We have solid, liquid, gas, and plasma. We don't really talk about the 4th one when it comes to weather. So anytime we go from a high energy phase to a low energy phase, we are going to release heat. We are going to be cooling. Anytime we go from a low energy phase to a high energy phase, we have to absorb heat. We're going to a higher, hotter state. So if we go from solid to liquid, we are melting the solids, and therefore we have to absorb heat to get to that liquid phase. When we go from liquid to gas, again, we have to absorb quite a bit of heat to vaporize that liquid to go to the gas phase. In the other direction, if we're going from gas to liquid, we are freezing, we are solidifying. It's condensation is what the actual term is. We are condensing that gas down into a liquid. We are slowing down those molecules, so we are releasing heat. When we go from liquid to solid, that is where we are freezing. Again, we are really slowing down those molecules and releasing more heat. The Earth is in balance, energy is in balance, so we absorb our energy we have incoming solar radiation, and then that radiation is used in different ways. Some of it gets reflected, some of it gets absorbed, some of it gets, transmitted, and then we also send additional heat back to space. So we have incoming and outgoing are going to be about the same because we are taking some of the heat from the Earth and releasing it. We will see later on when we look at climate that we actually have more heat coming in than we're losing, so we're actually going to be absorbing some of that heat. But we have to be in some sort of a balance. We're not creating heat. We're bringing the heat from the sun. So we've already used many of these terms, but I'm going to define them now. So force is acceleration times mass, F equals ma. So your weight is actually a force where the acceleration is the acceleration due to gravity. Newton is the unit for force. So a Newton is going to be a kilogram times meter over second squared. So kilogram is going to be the mass, Meter over second squared is the acceleration. Work is done when energy is expended or force is used, so that will be force times distance. So the unit for work will be joules or Newton meters, or kilograms times meter squared over second squared. Power is the rate of work measured in watts, so a watt is a joule per second, or kilogram times meter squared over second cubed. So when we're looking at the Earth, we're looking at massive amounts of energy. So we're talking like exojoules, which is quintillion joules, 10 to the 8 joules. I think that might be the wrong number, but anyway. So we're talking about massive, massive amounts of energy. Whereas we talk about, a light bulb uses 60 watts. So watts is joules per second. So we're talking massive amounts of energy when we're talking about the planet. So the energy for our planet comes from the sun. This will be as electromagnetic energy. We talked about this in the first few weeks of class when we were talking about astronomy. So EM energy is radiated as a wave. It can also come as particles. Those are photons. The wavelength is going to determine the amount of energy and the color in the case of visible wavelength. So longer wavelengths are lower energy, shorter wavelengths are higher energy. And wavelength is the distance between those waves. So the closer they are together, the more energy we have. We have three options for incoming energy. It can be redirected or reflected. It can be transmitted, which means it makes it through the atmosphere. And then it can also be absorbed. It can be absorbed in many places. Absorption means that it causes the molecules to vibrate. The ratio between reflected and absorbed is called the albedo, and it's going to be an indication of temperature. So high amounts that are reflected compared to absorbed are high albedos. This happens when we have light colors. It will reflect more. So something that is white will reflect more energy. Low albedo is when we have more absorbed than reflected. This happens when we have dark colors. So this is the reason why people put a silver reflective screen in their windshield during the summer, because that silver will reflect more of the energy, which will keep their car cooler. Low albedo, dark colors, that's why black cars heat up faster than white cars. We'll talk more about albedo when we talk about climate as well. The atmosphere is the gas layer above the solid Earth. So this is the reason why Earth is habitable. It's not just that we have an atmosphere, it's that we have our specific atmosphere. Many planets have atmospheres. Most atmospheres are not going to be conducive for life as we know it. Our atmosphere is also where we're going to generate weather, which is why we're talking about it today. There are many, many gases in the atmosphere. We will talk about this several times. Nitrogen, oxygen, and argon are the primary permanent gases that make up the most of the atmosphere. Nitrogen is over 78% of the atmosphere. Oxygen is a little shy of 21% of the atmosphere. Argon is a little less than 1% of the atmosphere. The rest of the atmosphere are these variable amounts. So we have water vapor, carbon dioxide, and then others. Water vapor we will see is very important for weather. Carbon dioxide and some of these other gases will be important for climate. And we will talk about that in the final week of class. Humidity is the amount of water vapor that we have in the air. So warm air holds more water than cold air. Relative humidity is the ratio of water vapor present to the maximum possible for that temperature. So warm air can hold more water vapor than cold air. So if we will see today that if we take air that was warm and has a high amount of water vapor in it, and we then cool that air, the relative humidity will go up because the cold air can't hold as much water vapor as the warm air. So the closer we are to 100% relative humidity, the closer we are to having rainfall. We have evaporation of water coming from Earth's surface, which can contribute to the water vapor in the... Sorry about that. I will go try to get them to quiet down. So evaporation from the Earth's surface will contribute to the amount of water vapor in the atmosphere. Some components of the atmosphere will be variable, so these will change percentages. This is going to be important for global climate, which we will talk about in the final week of class. But we can also have impacts on weather, particularly if the amount of water vapor varies. Some components in the atmosphere are not gases, so we have aerosols, which are solid particles that can absorb, reflect, or scatter incoming solar radiation. They can help with cloud formation. They also can help with cooling the planet. And then again, aerosols will help with cloud formation, and then they can also help with global cooling. We will see this in week 16 when we talk about climate. Ozone is an important part of the atmosphere. Ozone is where oxygen takes the form of O3 instead of O2. There's a layer of ozone 10 to 50 kilometers above the surface. This is an important layer in the atmosphere because it's a protective layer that it turns out is unevenly distributed around the globe. You may have heard the term the ozone hole in the ozone layer. Parts of it are thinner. This layer helps regulate solar radiation. Without the ozone layer, we would have too much solar radiation that makes it to the surface. One of the other variable components that we have is carbon dioxide, which we actually see here in this graph. We see the up and down of the annual or seasonal rather variations in carbon dioxide. We will talk about this up and down is due to photosynthesis during the spring and summer, which consumes more carbon dioxide because plants take in carbon dioxide and then release oxygen. But we will talk a lot more about carbon dioxide in week 16 when we're looking at how the variable gases in the atmosphere impact global climates. So the atmosphere is layered, like most things on Earth. It's difficult to define its upper limits. The place where we spend all of our time is called the troposphere. This is the 8 to 12 kilometers above the Earth's surface. Some air travel can get out of the troposphere, but not much. There's a rapid decrease in temperature with elevation in this layer due to the decrease in air pressure. This is also where all of our weather will happen. So we have clouds in this layer that is condensed water vapor. This figure is going to show us the different layers. So each layer will be separated from the next by a pause. So each sphere will be separated from the next sphere by a pause. The ozone is going to be in the middle of the stratosphere. I'm sure that's a word you've heard. We see that in the troposphere where we live, the temperature drastically decreases. That's what this yellow line is as we get to the top of it. It then settles and stays pretty consistent for the lower part of the stratosphere, and then it drastically increases. And then it will settle a little bit at the bottom of the mesosphere, and then it drastically decreases. It gets even colder. It settles, and then it will severely increase as we get into the thermosphere. So the troposphere is the lower 8 to 12 kilometers of the atmosphere. It is bounded by the tropopause. This is where we stay. The rate at which the temperature decreases with elevation is called the environmental lapse rate. The thickness of the troposphere will vary with latitude and with season. The next layer up is the stratosphere. The upper limit of the stratosphere is called the stratopause. It has a fairly consistent temperature for the first about 20 kilometers. This increasing temperature above that is due to the ozone being concentrated in that about 30 to 50 kilometer range. The next layer up is going to be the mesosphere. Its upper limit is the mesopause. Here we will see the temperatures decreasing. The coldest temperatures will occur near the mesopause. And so again, this is decrease in pressure. And then the upper part of the atmosphere is the thermosphere. It doesn't have a defined upper limit. Here the temperature will just keep increasing. Here temperature is going to be defined by molecular movement. So if you had a thermometer there, it wouldn't actually read these temperatures. we're defining that temperature by how fast the molecules are moving, because the faster the molecules move, the higher the temperature. But there are very few molecules at this temperature, so they are moving extremely fast. So it's a kind of an academic definition for the temperature. This is, these increasing temperatures at different layers is why we have heating on re-entry into the atmosphere. It gets very hot as objects come to Earth. Atmospheric pressure is basically how much weight the air column is. So barometric pressure, it's called that because the instrument we use to measure it is a barometer. The barometric pressure is the weight of a column of air. So the higher we are in elevation, the less air we have on top of us, the less molecules, so the pressure will decrease. That's why your ears pop when you go up to elevation. It's also why you have a harder time breathing at high elevations, because there's less oxygen available. The pressure can also change due to temperature changes, so cold air is more dense than warm air, so it tends to have higher pressures. And we will always see that pressure will move from high to lows. These pressures will influence global circulation. Sorry for my pause there, which you didn't notice because I paused my recording. So cold air is more dense than warm air, so it has higher pressure. We are going to see when we talk about actual weather patterns, however, that we typically associate high pressure with warm air masses and low pressure with cold air masses. So please don't be confused by this. But this is why cold air feels heavier than warm air. And then this pressure will influence global circulation, which we will see as well. So let's see here. Pressure will decrease as we go up in elevation. That's what actually both of these figures are showing us, because we will have fewer air molecules basically packed on top. So our energy is coming from the sun. It's coming as EM energy, and it's being redirected in all these different ways. That energy is going to hit the Earth in a variety of ways, because the Earth is a sphere. The Earth is a tilted sphere that's also rotating, and it's orbiting the sun. So that means we get variations in solar radiation across the planet and at different times of the year. So rotation is the spin about the axis. This is why we have day and night. The circle of illumination separates the dark versus the light hemispheres. The orbital rotation is going to be the circumnavigation about the sun. So this is the revolution of the planet. This is what makes our year. Depending on our distance to the sun, that will impact whether or not we have the length of our days, as well as our seasons. So we have 4 days that we will talk about. We have 2 what are called equinoxes. So we have one in the spring and one in the fall. That is the point where the sun is vertical over the equator and everywhere has an equal amount of day and night. And then days will either get longer or shorter depending on which direction the Earth is going and which hemisphere you're in. We have a solstice in June. In the northern hemisphere, we call this the summer solstice. In the southern hemisphere, it would be the winter solstice. The June solstice in the northern hemisphere is the longest day for the northern hemisphere. That is the day when the sun is hitting the 23.5 degrees north latitude at a vertical angle, and so it's the longest day for the northern hemisphere. The other solstice, it occurs in December, December 21st to the 22nd. This is going to be the shortest day in the northern hemisphere. It will be the longest day in the southern hemisphere. This is when the sun is hitting the 23.5 degrees south line of latitude at a vertical angle. And so this angle of the sun with the horizon is going to impact the amount of light that we get at different times of the year, and that's going to impact our weather pretty drastically because it's determining the amount of energy. So why do we have seasons? The solar radiation varies with location in orbit and the tilt of the planet. The distance to the sun is actually fairly minor. We will see that we can have winter even when we're fairly close to the sun, when we're at our closest to the sun. The more important thing is the tilt of the planet and the length of the day. So those are going to be controlled by the angle of the sun hitting the planet. So this is going to determine what part of the planet gets, or the amount of the atmospheric rays, the angle that the sun's rays hit the planet is going to determine how much atmosphere they must go through. So we can see that these rays that are hitting at higher angles, as they're hitting the further extreme latitudes, they are coming in at an angle. So they are having to transverse much more of the atmosphere, so we're going to lose more of our solar radiation, and it's also being spread out. So we can see that with this flashlight demonstration, that if we angle our flashlight, our beam is less concentrated, it's spread out more. The same thing happens with the solar radiation, so that's why we have such a difference between the equatorial regions and the polar regions. So the Earth's axis is inclined 23.5 degrees, which is why those lines at 23.5 degrees north and south, which are the Tropic of Cancer and the Tropic of Capricorn, are so important. The other line that's important are circles. So the Arctic Circle and the Antarctic Circle, those are going to be the places where beyond those we can actually have periods of more than 24 hours of darkness. So this tilt explains why we have seasons in the opposite hemispheres, or opposite seasons in the opposite hemispheres. So in the summer for the northern hemisphere, in June, this is when we're going to have basically our start of summer in the northern hemisphere, the summer solstice. So the rays, actually the solstice is the longest day, so that's not technically the start of summer. That's not technically the start of summer. So the rays at this point are going to be perpendicular to the Tropic of Cancer. If we look at this, we can see that areas south of the Antarctic Circle at this point are not getting any light. We see our circuit of illumination here. The winter solstice is when the sun's rays are perpendicular to 23.5 degrees south. So in this case, it's the opposite situation. So we're going to have shorter days in the northern hemisphere, longer days in the southern hemisphere. At this point, the South Pole is getting all light. And areas north of the Arctic Circle are getting no light. The equinox happens in March and September, and that's when the sun's rays are going to be perpendicular to the equator. Days and night will be equal everywhere. And so everywhere will get equal amounts of day and night. So we can actually determine the length of daylight based on our latitude and our time of the year. So on the equinoxes, we're always going to have 12 hours of day and night in every location. That's what the equal night, nox means equal night. On the summer solstice, at the equator, we have even amounts of day and night. Everywhere else, we have varying amounts. So as we get further and further north, we will have one period where, once we get past that circle, either Arctic or Antarctic, we will have periods of only summer or only winter, only light or only night. So this chart is from your lab manual. You will see that you only have daylight, at 70 degrees, you have 2 months of just daylight. At 90 degrees, you have 6 months of daylight. So this is all due to that tilt of the Earth. Here's an example of this. So if we go to extremely northern latitudes, we can actually see the sun basically doesn't set for a period of time. So this is what we call the midnight sun. So this is showing that 2 months of daylight in Norway that we see, that the sun is not truly setting, it's just lowering in the horizon. It's really disorienting, I might add. I only spent a few weeks in 24 hours of daylight, but it's very disorienting. Heat versus temperature. So heat is thermal energy, so this is the energy from internal motions of molecules. The faster the molecules move, the more heat we have. It's a quantity of energy. Whereas temperature is the average kinetic energy of those molecules, so it's the intensity of the energy. It's a fairly subtle difference. Mostly we will measure heat by temperature, but there is a slight difference here. When we move heat, we are basically just transferring energy. Heat will always move from high to low, hot to cold. Everything wants to go from high to low. You're going to see that over and over again as we're talking about weather. Heat can do this in 3 ways. We can have conduction. We've already talked about conduction, right? No, I'm sorry. We haven't talked about conduction. We've talked about convection. So conduction is the transfer of heat by moving through a substance by atomic or molecular interaction. So in this analogy of boiling water on a stove, conduction is the pot metal heating up. Convection is the transfer of heat by moving material. So we actually move physically hot material. So in our analogy, it's the hot water moving up to the top of the pot to displace the cold water. Cloud formation is an example of convection in weather processes. We talked about convection a lot with plate tectonics, remember. And the final one is radiation. So this is wave-like energy that's emitted by any substance that has heat. We actually emit radiation as well. Sunlight is radiant heat transfer. Electromagnetic waves are radiant heat transfer. So this is the energy that's coming off the hot burner. We can see the color changing, and we can actually feel the energy coming off if we get close to it. So again, radiation is the electromagnetic spectrum. The speed of light is 3 × 10⁸ meters per second. The individual colors of light have different wavelengths. They're traveling at that same speed, but their wavelengths will basically determine what their color is. So the wavelength is how close together the waves appear. So visible light is between 400 and 700 nanometers for its wavelengths. Infrared are longer wavelengths. This is what we detect as heat. So the 700 nanometer wavelengths are the red side, the 400 is the violet side. So ultraviolet is shorter wavelength, so this is higher energy. This is the stuff that causes sunburns. UV radiation, this is, that's why you're looking for sunblock that's UVA, UVB. It's blocking this ultraviolet radiation. Our ozone layer blocks ultraviolet radiation. So laws of radiation, all objects at whatever temperature will emit radiant energy. Okay, makes sense. Hotter objects radiate more total energy per unit area than do colder objects. Also makes sense. If it's hot, it has more energy. Hotter objects radiate more energy in the form of short wavelength radiation than do cooler objects. Okay, hotter objects have shorter wavelength energy, which is higher energy. Makes sense. Hotter objects will be more towards the violet end of the spectrum. Objects that are good absorbers of radiation are good emitters as well. So if it can take in energy, it can release energy. Okay, all this makes sense. Basically, very hot things will be towards the blue and violet colors. Cold things will be towards the red. Which is rather fascinating because typically when we talk about hot and cold, we do the opposite, right? But it's not actually true. What can happen to this incoming radiation? So we can have things absorbed. So we can absorb in the cloud layers. So basically we make the molecules start to vibrate within the clouds. We can also have absorption after we transmit through the atmosphere, so it absorbs on the ground. We can have transmission through the atmosphere that actually reaches the ground surface. And then we can have reflection and scattering. So we can have reflection before it even really gets into the atmosphere. That's called backscattering. We can have reflection from our cloud layers. And then we can also have reflection from the surface. So basically, there are many paths this energy can take. And again, we're in a balance of some sort. So we can have these different paths. We see that about 30% of our incoming radiation is lost to space by both reflection and scattering. And then we have about 20% gets absorbed by the atmosphere. So about 50% makes it to the ground and then is being absorbed and used by the ground. So Albedo is going to be the difference or the proportion that's reflected versus absorbed. So more reflection is a higher albedo, so light colors will reflect more. So this graphic is showing us the different types of albedos. Water can actually reflect a lot of light depending on the angle it's hitting. Snow has very high reflective properties. So if you are in snow-covered areas, it's actually really important to use sunscreen. Especially underneath your nose and chin, because you have this reflected light coming up at you constantly. So you can get some pretty nasty sunburns. Dark colors will absorb more. So that's why if you have a black asphalt street, it will be much easier to clear than a concrete street. It warms up faster. I'm not even going to go into my windshield screen example again. Greenhouse gases. We'll talk more about these in week 16, but this is what basically we have incoming energy gets absorbed in the atmosphere. Outgoing energy can also be absorbed in the atmosphere, and that's what greenhouse gases do. So certain gases will trap that outgoing energy. Two of the big ones that do it are water vapor and carbon dioxide, which are both pretty common in our atmosphere. So if this energy gets trapped by these gases, it gets radiated back to the earth, which ends up increasing the temperature. It's a very natural process. It can be increased due to human activity. We don't really see this happening at all on the moon because the moon doesn't really have an atmosphere. If we look at a planet like Venus, we see extreme greenhouse gas effect because of its atmosphere. So almost all the energy gets reflected back, which is part of the reason why it has such a high temperature. So it's natural, but we are making it worse, and we'll talk more about that in week 16. Temperature and how it varies. So incoming radiation is going to be determined by latitude. So the angle of the sun and how much sun actually makes it to the surface is going to be determined by our latitude. The surface material is also important. So land will absorb more energy than water, so land heats up more than water. Altitude is also important. So the higher up we are in the troposphere, elevation-wise, the temperature is going to drop. So temperature drops with elevation in the troposphere. Local geology can be important. This will determine things like exposure to wind, the distance to water bodies, things like that. And then albedo. So those material colors. So light surfaces, including clouds and ice, reflect more energy, so we have lower temperatures. Dark surfaces will absorb more. So here we have an example of several different locations, including St. Louis, Missouri, I might add, and their temperatures throughout the year. So when we look at Peru, this is close to the equator. We don't see a lot of variation in the temperature throughout the year because it is not seeing a terrible amount of variation in the incoming solar radiation. When we look at places that are close to coasts, we see less variation. So Cape Town, South Africa, for example, is close to water. It's surrounded by water, so that water helps regulate the temperatures. We see less variation compared to St. Louis, which is close in value to the latitude, just in the opposite hemispheres, but St. Louis is in the middle of land. So that land surface leads to more variation in the temperature. So when we go to even further north, we basically will start to see the temperature start getting colder and colder and colder. As we get further north, we can see that we have these very cold temperatures during the winter periods when we have less and less light. So at 71 degrees north, we are actually north of that Arctic Circle. So there are periods of time when there is no light. And that for Alaska in the northern hemisphere would be during the January and December months. So this is a map showing us global temperatures in January. And so January again is the northern hemisphere's winter, the southern hemisphere's summer. So we can see that the northern hemisphere has colder temperatures because we're having less light coming in. Those areas north of the Arctic Circle have very little or they have no light rather coming in, so it's quite cold. We see this interesting pull up in temperature here along the coast of Europe, along the eastern edge of the Atlantic Ocean. This actually has to do with the ocean currents. We see several of these around the globe where we have these pull-ups. there is actually a warm current that flows in this area, and it keeps the water warmer than it otherwise would be, which keeps the land surface warmer. We don't see the same thing happening on the western coast of the Atlantic because it's cold water that's flowing here. So we're going to see that the equator tends to be pretty consistent. The next one will show us in July. The equator is not going to change very much, but we're going to see basically a flip in the pattern, that we're going to see the hotter colors in the northern hemisphere, the cooler colors in the southern hemisphere. Another thing to note, the northern hemisphere has a lot more land surface, so it's going to have more drastic temperature variations, whereas the southern hemisphere doesn't have as many large land masses, aside from Antarctica, which is covered in an ice sheet. Whereas there's a lot more land in the northern hemisphere. So if we now look at July, so this is the northern hemisphere's summer, the southern hemisphere's winter, again, we see that the equator is pretty consistent. We don't see as drastic of a pull up here, but it's still somewhat of a pull up along the eastern edge of the Atlantic Ocean. There's not as much variation in the southern hemisphere because, again, there's not as much land, so the oceans are much more consistent. So if we compare this, there's a lot more variation in the northern hemisphere's winter and summer than in the southern hemispheres. So I am now going to basically give a preview of next week, which is weather. I didn't want to go into nearly as much detail about the layers of the atmosphere as your textbook does. I will admit, meteorology is not really my thing. I don't feel confident going into extreme detail with it, so I'm giving it at a more broad overview. Sorry about that. So now we're going to talk about weather, which is one of the important things for understanding the atmosphere. So weather is very much controlled by clouds. So clouds will develop when we have small water vapor droplets or ice crystals condensing from the atmosphere. Clouds will be responsible for rain, snow, thunder, lightning, rainbows, hail, but basically all of our weather. Cumulus clouds are puffy fair weather clouds. Cumulonimbus clouds are thunderstorm clouds. Your book goes into a lot of detail about the different cloud names. One of the things that will make clouds form is that, remember I mentioned that warm air can hold more moisture than cold air? If warm air the other thing I mentioned is that warm air is less dense than cold air, so it will want to rise. So warm air, which can hold more moisture, wants to rise. As it rises, it's going up to colder temperatures because it's colder in the troposphere. That will make it cool down, which means that now its relative humidity will go up because it still has the same amount of water vapor in it that it had when it was warm, but now it can't hold as much. So the relative humidity goes up, and that's what can lead to these clouds starting to form. It's going to force condensation. So weather processes are very important for looking at differences in pressure and temperature. So the main processes that are going to control these are going to be atmospheric pressure, which I've already talked about, circulation patterns, vertical stability, and the Coriolis effect. So circulation patterns develop globally. We have warm air masses at the equator, which have low pressure. Warm air has less pressure. So basically we have these low pressure centers at the equator. So air wants to flow into these low pressure centers. It's warm air, so it's going to want to convect upward because it's less dense. It has moisture in it at this point. It will cool as it rises, which will increase the relative humidity. The water vapor will start to condense, and it will form clouds, and eventually will drop its precipitation. So that's what we're seeing in these cells here. So that's why we will have areas of belts of intense vegetation along the spot where we have these intense amounts of precipitation. The air in the troposphere will now be dry and it's cold, and that makes it more dense, so it will start to sink. It sinks around 30 degrees, both north and south. This is dry air. And so that means we will have a desert around that 30-degree mark because there's no moisture in that air. So this are what we call subtropical mid-latitude deserts. There's a similar pattern that will happen centering around the low pressure zone at 60 degrees. It's less drastic because we have less extreme temperature variation, but we see these two cells of patterns. And And so we're basically seeing these low pressure centers around the equator, a high pressure center around 30 degrees, and then a low pressure center around 60 degrees, and then high pressure at the pole. And then we're seeing a cross section of that here. So this can explain some of our global patterns, our distributions of intense vegetation where we have the intense rainfall, and deserts where we have those cold air descending. Another circulation pattern is the jet stream. So the jet stream is, instead of looking at vertical circulation, we're looking at circulation around the globe. So the jet stream is a mid-latitude air mass it occurs where mid-latitude air masses of different temperatures meet. So we have two. We have a polar jet stream where Arctic air meets subarctic air, and then we have a subtropical jet stream where the subarctic air meets tropical air. The polar one will be stronger because it's a stronger contrast. These will form as westerly winds, so we're flowing from west to east. The westerly flow in the northern hemisphere is due to the Coriolis effect, so the spin of the planet. This is why in the United States we tend to see weather patterns move from the west to the east. They're moving with the jet stream. The greater the difference in temperature between the two air masses, the faster the jet stream will flow. The polar jet stream is about 10 kilometers in elevation. The subtropical is about 13 kilometers in elevation. The jet streams control where we have peaks and troughs, and this can control high and low pressures. And we'll see this is important for frontal systems. So the peak flow of the jet stream is about 2 times the wind speed. So we will see that the polar jet stream, for example, in winter is much faster than it is in summer because we have a greater temperature variation. It's about 100 to 500 kilometers wide and several hundred kilometers thick. The boundary between that Arctic and subtropical air is much stronger, so that's why the polar will always be stronger. The severe weather locations will be controlled by shifts in the jet stream, so we will see the low pressures and high pressure centers will move the jet stream. So here we can see that we get ridges in the jet stream when we have high pressures and troughs in the jet stream where we have low pressures. So pressure centers are areas where we're going to have air flowing in or air flowing out. So if air flows into a region, it causes convergence. The air will pile up and it will increase pressure. If air is flowing out of a region, that means that we will have a loss of pressure, and so we will have a decrease in pressure. So that may sound weird when we then talk about which are high pressures and which are low pressures. So air wants to move into low pressure centers, so it will be pulled into the low pressure center. That low pressure center then will push the air aloft, and then it will move away and it will diverge. So that is why we have divergence associated with a low pressure system, even though air flows in at the bottom. So when we're talking about the divergence and the convergence, we're talking about at the top, above these centers. When we have high pressure centers, the air wants to leave. So the air is being pulled in from the top and it's going to pile up, which will increase pressure, which it then wants to leave, and so it will be diverging at the bottom. So these first two sentences are indicating what's happening aloft. So the combined temperature and air movement will produce these low pressure centers, which are marked by L's, and high pressure centers, which are marked by H's. High pressure centers tend to produce a ridge in the jet stream, so it pushes the jet stream north. Low pressure centers produce troughs, so it pulls the jet stream south. So on here we would see this is a high pressure center, this is a low pressure center. And this is why meteorologists often talk about the location of the jet stream and how it's controlling our pressure centers. Vertical stability is movement of air in a vertical sense. So we could have movement of air due to temperature variations. So stability is the tendency for a parcel of air to want to move or remain stationary. So if the air is in equilibrium with the air around it, it will not want to move, and that means it's stable. If the air is not in equilibrium, so if it's either hotter or colder, it will want to move until it's in the same state as the air surrounding it, and that is when we have unstable air. So We commonly have instability when light, warm, moist air is overlain by dense, cold air. So that moist air is wanting to move. So it will cause parcels to sink or rise. Severe weather is often associated with atmospheric instabilities. The Coriolis effect is the uneven distribution of solar radiation between the equator and the poles. So we have differences in pressure and temperature gradients. We also have the Earth spinning. So air will not follow a straight path. The straight path is deflected due to the rotation of the Earth. So Earth rotates west to east. So Earth rotates counterclockwise when you view it from the North Pole and opposite when you view it from the South Pole. The Coriolis will deflect things to the right in the northern hemisphere and then to the left in the southern hemisphere. So that's what we're seeing here, that we will always move to the left in the southern hemisphere, to the right in the northern hemisphere. So we get cells produced by areas of high and low pressure that will follow this deflection due to the Coriolis, and that will establish our predominant wind patterns. So we tend to have wind patterns that follow this Coriolis effect. A front is what's going to generate weather. So a front is a boundary between cool and warm air. There are two ways this can happen. We can have a cold front where we have cold air is moving into a mass of warm air. What happens here is that, remember, warm air wants to rise because it's less dense. So if we are pushing cold air into warm air, we are very quickly pushing that warm air up above the cold air. And so it will have a very fast lift, and so we will generate clouds very quickly and condensation very quickly. So severe, fast weather is associated with cold fronts, cold air moving into warm air. A warm front is where we have warm air moving into cold air. Again, the warm air wants to rise, but when the warm air is moving into the cold air, it can go much more gradually up into the atmosphere, and so it's generally fair weather. So this is nice, pleasant weather associated with warm fronts. So the warmer air is always going to be lifted by the colder, denser air. How fast it lifts is going to determine whether or not we have severe weather. Both of these will have different humidity, stability, and densities. Again, we have severe weather typically associated with cold fronts. A stationary front is where we don't have a lot of movement between the cold and warm air, so they are going to be indicated by a mix of the two symbols. And then we can have a occluded front. This is a special case where we have rapidly cooling air overtakes colder air, and so you end up getting cold or warm air wedged above the boundary. So this can lead to spin and some pretty severe weather. We can have hazardous weather as thunderstorms. So thunderstorms happen across the globe, especially in equatorial regions where we have more moisture available. In order to have thunderstorms, you have to have warm, humid air in the lower atmosphere that can then be pushed very quickly up into the upper atmosphere along a steep vertical gradient. And updraft force helps force that moist air to the colder levels of the atmosphere. So it's very common to see these in long cold fronts. This map is showing us the average number of days of thunderstorms in a year. So we can see that as we move south, we get more and more thunderstorms. So the way a thunderstorm develops is that we will have moist air is going to be forced upwards, and it will cool and then will form a cumulus cloud. Because remember, it is going to have lower relative humidity as it's forced to cooler temperatures. If the moisture and the updraft continue, the relative humidity will continue to increase and the cloud will grow. The upward growth of this cumulus cloud is called the cumulus stage. As the cumulus cloud continues to grow, it will become a cumulonimbus cloud. This happens when we have release of latent heat from the water from the water vapor condensing down to water into the cloud. So we're basically now have heat, so we have energy. During the mature stage, the dome and the tower will grow and precipitation will start. So water will freeze into ice and snowflakes in the upper portions of the cloud. The larger snowflakes will fall and they will melt as they go through warmer air. They are falling because they can't be supported by the updrafts anymore. In the lower cloud, these large liquid drops can collide with one another to coalesce into larger raindrops. The rain will fall when it can no longer be supported by the updrafts. So the mature stage, this will occur. We'll have our updrafts pulling moist air up into the upper part of the cloud to develop our precipitation. We will also have downdrafts and falling precipitation leaving the base of the cloud. So basically we have circulation within the cloud. This will continue to grow until it reaches the top of the unstable atmosphere that we're not having vertical movement anymore. The updrafts will actually start to build out into an anvil shape, and this is when we start getting into the dissipating stage. So we have heavy rain, lightning, thunder, hail can all be during this stage. And then the dissipating stage is when that upward supply of moist air gets blocked by the downdrafts. So they're no longer in balance. The downdrafts overpower the updrafts, so we're not pulling new moisture up into the cloud. And so those downdrafts will bring cool, dry air because we no longer have that moisture up in the cloud. We're not bringing new moisture up. And this will cause some of the precipitation to evaporate. That evaporation will further cool our downdrafts, because remember, if you go from liquid to gas, you have to absorb some heat, therefore it makes it colder. And this will cool those downdrafts, and so it will further block the updraft of that warm, moist air, and basically the thunderstorm will have run its course at this point. A thunderstorm is considered severe if it is greater than 93 kilometers per hour wind speed, if it has large hailstones, or if it creates a tornado. Thunderstorms are somewhat self-perpetuating. As long as they have supply of that moist air and they're able to pull it up into the cloud, they will keep going. They will stop once they run out of that moist air. So we need large changes in wind shear to help bring that air up to the higher reaches. We need high water vapor content. If we don't have water vapor, we can't make the clouds. You need an updraft to bring that air up, and it's helpful to have a dry air mass above a moist air mass so that that moist air can then be moved up into the drier air. So vertical wind shear is where we have varying velocities amounts and directions as we go up in the troposphere. So we have an increase in wind velocity with altitude, and we have changes in the horizontal direction of wind with altitude. So this leads to a rolling motion of air in the lower troposphere. And so the greater wind shear we have, the greater the thunderstorms, because we are bringing up more of that air faster. There are different types of severe storms. So we can have mesoscale convective systems, MCSs. These are the most common. These are large clusters of self-propagating storms where the downdraft of one cell will lead to the formation of a new cell. They can last for 12 or more hours. We can also have squall lines. These are linear belts of thunderstorms. They tend to be quite long, about 500 kilometers. They will develop parallel to a cold front, but ahead of it. And then the most dangerous ones are supercells. These are the most damaging. We can have what are called mesocyclones, which is an upward spiraling column of air. These are capable of creating tornadoes. These are identifiable with Doppler radar, so this is when we're looking at that rotation on Doppler radar. They are smaller than either mesoscale convective systems or squall lines, but they're quite violent. And again, they can produce those tornadoes. And we are actually seeing a supercell here. Lightning is a side effect of thunderstorms. So lightning is a flash of light produced by the discharge of extreme amounts of electricity. It will heat the air to extreme temperatures, more than 30,000 degrees, which causes the air to expand, which rapidly produces a pressure wave, and that is thunder. So lightning produces the thunder, which is why thunder comes later. Also, sound moves slower than the speed of light. We can have two types of lightning. We can have cloud to cloud, so they will start and end in the thunderstorm or nearby clouds. And we have cloud to ground, where it actually connects with the ground, and that's the one most people are more concerned with. So the way that we develop cloud to ground lightning is that cumulonimbus clouds will grow high enough for ice pellets and ice crystals to form in the upper reaches. Movement between those ice pellets will build a charge, so we tend to get positive charge in the upper part of the cloud and then negative in the lower. Remember, opposite charges repel from one another. So the negative charges that collect in the lower part of the cloud will repel the negative charges from the ground, leaving a net positive on the ground below it. There will be a narrow column of electrons, which are negative charged, moving from the ground towards the positive charge because they are attracted. This is a stepped leader. I always try to say that wrong. That stepped leader branches downward, while a streamer of positive charge from the ground will move up, being attracted again to the negative charge at the bottom of the cloud from some sort of a tall object. This is why they tell you to avoid tall objects in lightning storms. As the stepped leader approaches, a spark from the streamer attaches to the leader, and that will complete the circuit. This is the lightning strike. A return stroke produced by a surge of heated air is the flash. And then we can have additional leaders and streamers follow the same path, so that's where we get the flickering. So lightning can strike the same place twice. It tends to follow the same paths. Hail is another thing that happens during storms. So hailstones are an individual large piece of hail. These are basically concentric rings of ice that will grow. So what happens is that you start off as an ice nucleus, so we have that frozen ice pellet high in the cloud. It will fall because the updrafts can't support it. So then liquid water will coat it when it moves lower in the cloud, either through melting or just liquid accumulating on it. It will then move up further in the cloud. It'll get caught in an updraft and it will freeze, and then it will get too big and fall. So it's basically this repetitive motion up and down in the cloud. So we have these concentric layers that form. They can be very large and cause a lot of damage. And hail does not need to happen only in cold weather. It can happen anytime it's cold enough in the cloud to have that ice forming, and we have that fast movement up and down within the cloud. Tornadoes are a storm that's going to be created when we have a vortex extending from the cloud to touch the ground. So they will form when we have large differences in atmospheric pressure over very short distances. Supercells are the main spawner of tornadoes, but we can get them in other places too. So what happens is we have wall clouds forming the lower portion of the cloud due to updrafts. This will start to spin, and this forms a funnel cloud. It's only a funnel cloud until it hits the ground, then it becomes a tornado. Dust, debris, water vapor, they get caught up in the funnel. If that vortex will touch the ground, that's when it's a tornado. The material caught up in the tornado is what gives it its color. The wall clouds and mesocyclones are not actually necessary to form a tornado. You can get them in other ways too, but they're the most common way. We can get suction vortices, which are very small, intense whirls within a larger tornado. There are stages to tornadoes. So the big tornadoes are when we are in the mature stage of the tornado. We have the shrinking stage where it's thinning out, tilting the funnel, and we have increased winds. And then we have the rope stage, which is the decaying stage where it's flipping back and forth. Every stage of a tornado is dangerous. They can go for long distances on the ground in certain cases. Many times they don't stay on the ground for a terribly long amount of time. They are always dangerous. So tornadoes can be diameters tens of meters to much larger than that. The wind speeds vary, and that's going to determine the size. They travel typically only a few kilometers, but they have been known to travel for hundreds of kilometers. And they can move very, very fast on the ground. So the scale we use is the enhanced Fujita scale, the EF scale. So we go from a 0, which is not really even a tornado, it's just fast winds, all the way up to an EF5. Any tornado will cause damage. You will have roofs damaged, you can have trees uprooted, you're having flying debris. There's a lot of damage whenever you have a tornado. Tornadoes actually occur more in the United States than any other country. It has to do with a combination of our weather, topography, and geographic location. Canada is the next most common occurrence of tornadoes. We have what we call a tornado alley. We also have Dixie Alley, which is the smaller amount of tornadoes down here. Tornado alley is this area of increased tornado activity. It seems to be moving. We do see movement in tornado alley. So you can get tornadoes anywhere even in Pennsylvania. So this is the Kenzua Viaduct Bridge that was hit by a tornado in 2003. Um, this was actually a fairly small tornado. I think it was actually only an EF1 or EF2. But it was intense and it hit this bridge broadside. This bridge did have a flaw. I actually saw this on a show called Mysteries of the Abandoned. I believe it's also been on Engineering Disasters. They rebuilt this bridge out of a more sturdy form of iron during its lifetime. When they did that, they did not change out the way that it was anchored to its moorings, its footings, and that was the weakness, that when the tornado hit it, it ripped it off these moorings and then just bent this iron like it was, cooked spaghetti. Part of it still stands and it's now a lookout point. And they left the rest of the bridge as just a testament to nature. Other weather patterns we have are blizzards. Blizzards are severe winter storms that have large amounts of falling snow and high winds. That's when we have a whiteout. For the US, the thresholds have to be greater than 56 kilometers per hour wind, visibly less than 0.4 kilometers, or last for more than 3 hours. We can also have ground blizzards, which is the wind recirculating previously fallen snow. So blizzards tend to come from the interaction between a low pressure trough and a surface low pressure system. So these are going to come from those low pressure systems. The wind chill is important in blizzards. Wind chill is the temperature that we feel due to moving air. This is where it gets very, very dangerous. Dangers of blizzards are things like frostbite, hypothermia, and then just regular accidents. So we tend not to name these types of storms. I'll talk more about these next week. But we do have some general names for storms that follow the same pathway. So a nor'easter is a particular storm that follows this pathway. The Alberta Clipper kind of follows this pathway. These don't get individual names typically, unless it's a very, very severe storm. We can also have ice storms. I personally think ice storms are more dangerous than blizzards. Ice accumulates on power lines, tree limbs, and those things then fall. Ice, whether or not you get ice or snow, is going to depend on the thickness of the layer of cold air. So if everything is cold, we get snow. So if it never has a chance to melt, it's always going to be snow. If most everything is warm, it's going to be rain. So it may be snow up in the clouds, but if it moves through a very thick layer of air, warm air, it will be rain. It's where we have this layer of cold air at the surface and warm air above it that we get these two dangerous conditions called sleet and freezing rain. So if the layer of cold air at the surface is slightly thicker, that we have warm air above that our precipitation is liquid for a time, but then it moves into that cold air and refreezes, that's where we have sleet. So that's where it's coming down as little ice pellets. Freezing rain is a very dangerous condition. This happens when we have a very thin layer of cold air that's basically making the surface very, very cold. So it's liquid precipitation that's coming down, and when it hits the surface, it instantaneously freezes. So this is where you get that coating of ice on everything. And so this is very, very dangerous. So that's what I'm describing in this text here. So if objects are at or below freezing and liquid precipitation moves through a thin layer of cold air, that liquid, when it hits the objects, will instantaneously freeze. And so we get a coating of ice on objects and roads and things. There are other weather-related hazards as well. Fog is when we have a cloud in contact with the ground. This leads to very low visibility. You can come upon pockets of fog very unexpectedly, especially in mountainous type areas. Fog will actually form daily when warm air rises and meets the cool air from the night. So warm air coming off the ground surface meets the cooler air from the nighttime. Droughts are where we have extended periods of unusually low precipitation that then produces shortages of water. This leads to food shortages as well. This is not just going to impact people, it impacts the entire ecosystem. So droughts are a pretty big thing. So this map is showing us extents of droughts in various parts of the country. We can also have windstorms. So this happens in mountains, seasonally downside or lee side of the mountains. So this is basically we only have wind. We don't have any clouds forming. We can have dust storms. Dust storms are when windstorms will pick up suspended dust. They reduce the visibility. They can pose a biologic hazard, so we can have spores and pollen within that dust. The dust can stay in the atmosphere for a very long time. This upper image is from Black Sunday, which was one of the more intense dust storms during the Dust Bowl. The dust from this event made it all the way to the East Coast and beyond. So dust from, Oklahoma made it all the way to Washington, D.C. And then we can have sandstorms, similar to dust storms, only now it's sand being transported. It tends to be transported a little bit lower because they're larger grains and it's going to be bouncing along. It's very abrasive. So a sandstorm can rip paint off of objects. Think about it. You sandblast to remove things. In hot areas, we have to worry about heat waves. So a heat wave, sorry, that did not come out right. A heat wave is where we have an extended period of extreme heat that's both longer and hotter than normal. This tends to be worse in areas where people are not accustomed to heat. So when Europe gets a heat wave, they feel it very, very much. Whereas places that are more accustomed to heat are more used to it, so it's not as much of an impact. Heat waves are always going to be more impactful on certain groups of people. Young people, old people, homeless, ill people. This is going to be true of any sort of weather phenomenon. These are associated with high pressure ridges. So they can either be dry or humid, and this is where heat index comes in. So dry heat is always much better than humid heat because your body reacts differently to heat depending on what the humidity is, and that's what the heat index is. The heat index is how your body perceives temperature. So that's what we see here. The actual air temperature is on the vertical, the relative humidity is on the horizontal. We can see that if we have low relative humidity, our temperatures are pretty much the same until we get to these really hot temperatures. So even at 96 degrees, it only feels like 101. Whereas if we have higher humidity, well, say we're at 70% humidity, that 96 degrees feels like 126 degrees to your body. And so when we have very, very high humidity, it does not have to be very hot for your body to think it's extremely dangerously hot. So if we have 95% humidity, at 90 degrees, your body feels that it's over 120 or it's 127 degrees. This is in Fahrenheit, I will add. So high humidity is always much worse on your body. Humans and weather. So agricultural processes can increase erosion and dust storms. We saw that with the Dust Bowl. We have problems when we allow certain building practices in areas that are prone to certain types of weather. So trailers and tornado-prone areas is not a good idea because they have no protection against tornadoes. There is a thing called the urban heat island effect. So large areas of pavement will increase temperature. We see this in cities of all sizes. So the next time it starts to get warm, like the summer, look at the weather forecast and compare temperatures in the city to the areas, outside the city. You will see that it's hotter in downtown proper than it is in the suburbs. We also will talk more about global warming and climate change in week 16, but we are increasing temperatures due to our actions. When it comes to what do we do about weather, it's important to understand weather. So our forecasting is actually pretty good, especially with Doppler radar. And as we get closer to the events happening, we get better and better and better at it. So nowcasting is even better than forecasting. This is our anchors being on 24/7. Things like tornadoes are fairly quick to develop, but typically we've already established a watch and warnings, and so we're ready for them. Watches will turn into warnings, so that's what we see here. The taco watch is I've got the ingredients. The taco warning is I've made my taco and I'm ready to eat it. So if you're in a warning, that's where you're like, all right, I'm in trouble. I need to figure out where to go. Mitigation often depends on minimizing effects. So this is going to be building codes. So where can you have a trailer? Where can you not have a trailer? Do you have to have a storm shelter? FEMA, the Federal Emergency Management Agency, has guidelines for many of these things. They also come out after major events to help. Ensuring facilities continue to operate during severe events is important. So making sure that you have some infrastructure that will allow power to remain on. So things like having your power lines not being in the air can help during a ice storm, that you don't lose power. Warning systems are important. Tornado sirens, for example. I I like to tell the story when I lived in Philadelphia, when I was actually looking at the house I ended up buying, a siren went off and it sounded exactly like a tornado siren. And I kind of like crouched down. I thought for a second, I'm like, wait a minute, I'm in Pennsylvania. The sky is perfectly blue. That's not a tornado siren. It turns out that the volunteer fire department that was just down the way from my house used sirens that had the exact same frequency as our tornado sirens here. So I got somewhat accustomed to hearing that noise. So now I am, a bit desensitized to tornado sirens, which is probably not a good thing. And then worst case scenario, there's always insurance. Insurance will cover most of these things. Insurance surprisingly doesn't cover floods, but it will cover severe weather typically. On a personal level, preparedness is very important. So know what to do during severe weather. What do you do when you hear those tornado sirens? Knowing the weather patterns themselves. So for example, the time of the year, knowing, okay, I hear a tornado siren, I look outside, the sky's looking kind of green, that's not a good sign. So knowing the area you're in is important. Having some supplies ready. So when I drive across country in the winter, I have a suitcase in the back of my car that has some cold weather gear in it, just in case. Dressing appropriately for both hypothermia and heat stroke. So I personally know I am fairly susceptible to heat. I have had sunstroke before, so I know I'm very susceptible to it. So I take precautions in the hot months in what I wear and then what I do, so that because I know I'm susceptible to it. Hypothermia, it's hard to recognize in yourself. It's something that you typically have someone else recognize in you. Don't go outside unless it's absolutely necessary. So be, aware of when the better times are to go outside. So taking a run in the middle of July in the middle of the day or in the middle of the afternoon, probably not the best idea. Maybe wait until evening, or better yet, take it first thing in the morning when the temperatures are going to be coolest. And adjust travel as necessary. Do you need to go out in that snowstorm? Do you really need to go out in that snowstorm? Maybe not. Maybe stay home. So now I'm going to show the pre-lab video for this week, which is air masses, mid-latitude cyclones, and weather. It's about 7 minutes.
Hello students, welcome back for another pre-lab video. This week in lab we're looking at air masses, mid-latitude cyclones, and weather maps. The first thing that we're going to cover this week in lab is the idea of an air mass, a really big package of air, usually about 1,000 miles or more wide and several kilometers thick. The origin of this air mass can end up determining its characteristics. For instance, air masses that originate near the poles tend to be cold. If they originate over the continents near the poles, they tend to be both cold and dry. On the other hand, if they originate over the ocean near the poles, then we end up seeing a more humid air mass. Down in the tropics, you would expect things to be warmer, and that is the case. If the air mass originates over the continents, that tends to be dry and warm, and if it originates over the oceans, it tends to be warm and humid. These air masses meet along boundaries that are known as fronts, and we can have either a warm front or a cold front. In either case, what ends up happening when the two meet is that the warmer of the two air masses moves up and over the colder of the two air masses. Warm fronts tend to have a relatively gentle slope, and you'll see sort of gentle precipitation that occurs over a longer period of time because these things tend to move a little bit slower than cold fronts. If it's a cold front, the front is steeper. Again, the warm air moves up, but it moves up quickly, and that encourages the growth of cumulonimbus thunderhead clouds. Heavy precipitation follows, and these typically move through an area relatively quickly. Where a cold front and a warm front meet, you can see the development of what's called an occluded front. This is where essentially the warm air is getting wedged from one side by a cold front and from the other side by a warm front. And as a result, as the cold front overtakes the warm front, you basically force all of that warm air up to higher elevation and end up producing a uniformly cold air system down at the ground surface and warm air aloft. We have different symbols for the different kinds of fronts. Warm fronts are the red half circles, and the cold fronts are the bluish triangles or points. An occluded front is the purple pattern that you see there, and a stationary front is that mixture of red and blue. Okay, so these fronts are related to larger scale systems called mid-latitude cyclones, and this is a low pressure system where the air swirls around that low pressure system as it tries to move from surrounding areas of relatively high pressure towards this central zone of low pressure. It ends up taking on a curved path due to the Coriolis effect. There's also a corresponding structure called an anticyclone, but we're not going to look at that right now. This is what a mid-latitude cyclone looks like from satellite view. You can see this large sort of comma shape to the clouds, and this is what it looks like on a weather map. Notice on this weather map that we have air pressure noted in millibars, with the big red L here in the middle of the lowest pressure. So that's where all the air is trying to get to. And as it moves in, it takes on a path that diverts it slightly to the right. So that's the Coriolis effect at work. We see a cold front emanating out, moving along toward the east and northeast. A warm front is moving there as well. Of course, the warm front is slower moving than the cold front. And we can draw a couple of cross sections across this weather map and imagine what it would look like if we sliced this open and looked at it from the side, say from point A to point E, or point F to point H. So here are those cross sections. The first one from point A to point E, you can see, takes us from a cool air mass across a warm front to a warm air mass, across a cold front to another cold air mass. The upper slice shows an occluded front, so that's represented with that purple color, and you can see that mass of warm air aloft and cool air below. Now, what do you think this is? This is the weather station model and standard symbols for the conditions at any given weather station. In order to understand this symbol, you should review this figure from your lab manual. It shows all the different coding components to each of these little station models. The central part of it is a representation of the part of the sky that's covered by cloud. The little prongs coming off show the wind speed. We also have symbols in there for the past weather and whether the air pressure is going up or going down. So, for instance, in this one we have 50 over here in the upper left. That's an indication of the current temperature at that site. The 42 refers to the dew point temperature. The half white, half black circle in the middle means that we have essentially half of the sky covered with clouds, about 5/10 of the sky. The 196 you see over here is a measure of the air pressure in millibars, but in order to save space, what they do is they end up dropping one of the digits off of this. So what that really means is 1019.6 millibars. And then the plus 18 that you see here with the little slash after that, that basically means that the air pressure has been rising over the past 3 hours. So that means that it's gone up by 1.8 millibars, and the slash indicates that it's rising. The little dot in the lower right indicates that it's been raining. For the final part of this week's lab activity, you'll be asked to take some weather data that's provided in this table for several different weather stations. So you're going to be given information about where the weather station is, the percentage of cloud cover, the wind direction, the wind speed, the temperature, the dew point temperature, the air pressure, and then the change in air pressure, as well as any precipitation that may have been happening at that site. So you're going to plot that information on a map, and you can see on this map that some of the stations have already been done for you, like Chattanooga here, whereas Birmingham, it completely lacks any information, so you'll be adding that information to it. You'll also be completing the isobars So like right here, for instance, we have an isobar that is incomplete, so you'll be using the air pressure information from the different weather stations to deduce what the overall air pressure looks like, and therefore what the overall mid-latitude cyclone structure is. That'll be a nice synthesis activity that'll tie together all these different forms of knowledge in one sort of graphical output. And then once you've made that map, you'll use that map along with the assumption that the cyclone is moving to the northeast, as they usually do, to make a weather forecast for several different locations. Good luck this week in lab. I'll see you next week for another pre-lab video.
So I do have to say that those weather map symbols can be quite confusing. So that is when I encourage you to definitely read that page very carefully. So that is all for week 14, talking about the atmosphere and a preview of weather. Week 15 will be looking much more at weather. So that is all for today.